We're now going to talk about something called Richardson's interpolation, and this is a technique that's used to actually generate high accuracy results while using low order formulas. So you can imagine us, for example, using the forward difference method for a first derivative, but then improving on it using Richardson's interpolation. However, to explain how it works, this is going to take a bit of time, so I'm going to take it slow and let's see how we get on. So essentially, remember that we're typically, when we interpolate something, we typically have a step size. So we can define that step size as delta x or just simply h. So this is the step size. We assume that for each of the step sizes, we have some approximation formula. So as you choose a particular step size for the algorithm that you're working with, you essentially have some formula. Let's call it n1 of h. So you actually have an approximation formula that's parameterized by the delta. So essentially, the smaller you make your subdivisions, for example, in the case of integration, the better the result, obviously. So we always want to have a smaller value of h as possible. So essentially, we have n1 of h, and this is approximating some constant m. Let's assume that we know what the result actually is. Now, since this is likely to be some sort of iterative procedure, we have truncation error. So we can express a truncation error in the following form. So we take the actual result and then we subtract what we got as the estimate, n1h. And we can actually rewrite this as a sum of power series. If we think of a certain number of coefficients, let's say we have coefficients k1, k2, and so on, we can rewrite this as k1 times h plus k2 times h squared plus k3 times h cubed, and so on. So we don't know what these constants are yet, but we're just making the assumption that it's possible to actually formulate the truncation error in terms of these constants. Okay, so we know that the truncation error is on the order of h. So unless there is a very large variation in the k constants, of course. So essentially what we can do then is we can make the following statements. We can say that m minus n of 0.1, for example, is approximately equal to 0.1 k1. And we can similarly say that m minus n of 0.01 is approximately equal to the order, so it's 0.01 k1, and so on. And in general, we can say that m minus n1, let's not forget the index here, n1 of h, is approximately equal to k1 times h. Okay, so I've ignored the other terms here because obviously they are much smaller than the first term. So you can make this kind of argument essentially. So now the our goal is to find an easy way to combine all these rather inaccurate approximations. So we have a bunch of approximations which are all O of h, so on the order of the subdivision that we're actually making, and we want to combine these approximations in a way so as to produce formula with a higher order truncation error. So we don't want a truncation error on the order of h, we want it on the order of, let's say, h cubed or something like that. So how do we do it? Well, let's suppose that we can combine different n1 of h formulas to produce a truncation error on the order of h squared. for example. So that is actually our goal. Let's suppose that we have a new formula. Instead of n1 of h, we actually have n2 of h, and we say that the actual value minus n2 of h, and let's suppose that we can now represent this without this k1 of h term, because now the error is on the order of h squared, so we can start with that. We can say that there is some k2, let's have them with a hat. So k2 h squared plus k3, once again with a hat, h cubed, and so on. So this is much better because the error is obviously much smaller. It's on a higher order, h squared here. So once again, we have a bunch of these unknown constants, k2 hat, k3 hat, and so on. And similarly, if we were to plug in actual values, we can say that, for example, m minus n2 of 0.1 is equal to, and here is a surprise, it's 0.01 times k2 with a hat. And similarly, if you had, let's say, m minus n2 of 0.01, then this 0.01 will get squared, and you'll get something like 0.0001 times k2 with a hat as well. So if these constants, sort of k1, the k1 here and the k2 with hat here, if these two constants are of roughly the same magnitude, then we can say that the n2 approximations are much better than the corresponding n1 approximations. So this interpretation can actually continue by combining the n2 approximations in a manner that produces the formulas with the order of h cubed, h to the fourth, and so on. So we can take it almost to infinity. So to see specifically how we can generate the interpolation formulas, let's consider the O of h formula for approximating the m. So let's suppose that, let's get back to this idea that m is represented as our approximation formula n1 of h plus the error stuff. So that's k1h plus k2 h squared plus k3 h cubed, and so on. So this formula is assumed to hold for all positive values of h. So we can actually replace the parameter h by half its value, for example. And then we have a second O of h approximation. So we have something like the following: m equals n1, and now we do h over 2, plus k1 h over 2 plus k2 h over 4 plus k3 h over 8, and so on. So what we can do is we can actually take this particular line and we can subtract it from the line above, and we can actually we can subtract it from twice the equation above to attempt to eliminate the term that actually has the k1 in it. So the goal here is that we take all of this. So I'm gonna actually number them. So if this is 1 and this is 2, so what we want to calculate is 2 times this equation minus the previous equation. So once you write that out, you end up with the following. You end up with m being defined as n1 of h over 2 plus, and here in brackets we have n1 of h over 2 minus n1 of h plus k2 h squared over 2 minus h squared plus k3 of h to the cubed over 4 minus h cubed, and so on. So essentially what we do is we define n2 as the following. We say that n2, if we just continue this idea, we define n2 as n1 of h over 2 plus n1 of h over 2 minus n1 of h. So that's essentially this first part, and we kind of throw away the higher order terms here. So the equation of a higher order for m is an OH of squared approximation. So essentially we have m now being equal to n2 of h minus k2 over 2 h squared minus, well, if you really must have the other terms, minus 3k 3 over 4 h cubed, and so on. So essentially we have an order of h squared approximation, which is what we wanted in the first place. So now that we've done all this writing out, let's actually look at a practical example. So remember that when we talked about the forward difference method with a step of 1, so we had h equal to 1, or we called it delta x, but we can call it h. So when we have we had this method with a step equal to 1, what we're trying to do is we had the function f of x being equal to 3x squared, and we wanted to find out the first derivative at a value x equals 2. Now we know that the value is actually 12 from analytics. So let's assume that this original formula, the original forward difference formula, has a error term of order of h. And then we're going to use Richardson's interpolation on these values to see if we can actually get a better approximation. So in the previous example, we found that when we had h equals 1, that gave us the second derivative at a point of 2, having the value of 15. So that was quite far away from the actual value of 12. If we now take h to be, let's say, 1/2, and we actually calculate this in MATLAB, you'll find that the first derivative at a point x equals 2 has the value 13.5, like so. So basically this implies that n1 of 1, remember the h gets plugged into the n1, has the value 15. And it also implies that n1 of 0.5, a finer approximation, has the value 13.5. And we have n1 of 1, we have n1 of 0.5, and this is something that we can now use in our formulas above. So we're going to define n2. So n2 of 1 is going to be defined as n1 of 0.5 plus n1 of 0.5 minus n1 of 1. Okay, so we can try plugging in these values, and what we're actually going to get is, surprisingly enough, the value of 12. And go ahead and plug in these values if you don't believe me. So essentially, this gives us a much better value, because the error, if we look at the errors in both of these, there is a 25% error for this one. There is a 12.5% error for this result, which is better but still not great. And for this result, the error happens to be 0. We get exactly the result that we want. So essentially what this shows once again is that Richardson's interpolation gives us a more accurate approximation.